Welcome to Math 273C. This is a course on geometric numerical integration. My name is Melvin Leok, and I'm going to try to give you a brief overview of the topics which are going to be covered in this course, as well as some of the motivation for studying geometric numerical integration and what it is at some high level. So what happens basically is that when you look at continuous dynamical systems, many times they have properties that are conserved by the flow. For example, the energy. Other times there are various symmetries, reversibility, monotonicity properties, and oftentimes associated with these symmetries are momentum conservation laws. So for example, when you have a mechanical system which is rotationally invariant, then the angular momentum is preserved. If you have a mechanical system which is translationally invariant, then the linear momentum is preserved. And if you have a fluid system which exhibits what is known as the particle relabeling symmetry, then it exhibits the Kelvin circulation theorem, which basically says that if you take a material loop in the fluid and you would vect this by the flow, then the circulation which is enclosed within that is a constant of motion. With Lagrangian Hamiltonian systems, there is also a geometric property known as the symplectic form, and that is preserved by the flow of such Lagrangian Hamiltonian systems. And associated with that is this idea of integrability, which more or less says that if you have sufficient number of invariants of motion, then that guarantees that you can explicitly compute the solutions in terms of certain types of integrals. At other times, the equations themselves are defined on a curved manifold, such as a Lie group or more general configuration manifold. And what you would like then is you would like to construct numerical methods that respect that and automatically stay on those manifolds. This is not always so straightforward, because if you look at the conventional methods like the Euler method or more generally Runge-Kutta methods, then there's an implicit assumption that you're working on a linear space. And this is potentially problematic because there's no guarantee that the equations of motion are defined off the curve space, and when you use these kind of linear space techniques, you are in some sense moving off that configuration manifold. All right, so what's the motivation for studying these kind of structure preserving methods? One of the main goals, if you will, geometric integration, is that structure preservation gives you a means of reproducing long time behavior. What do I really mean by that? What I mean is that you have numerical methods which exhibit a discrete conservation law, and this gives you long-time numerical stability to computations, since what essentially happens is that the structure preserving algorithm exactly conserves some sort of approximation of the continuous invariant, which is always close to this continuous invariant which you're interested in. So as an example, if you look at what are called symplectic methods don't exactly preserve energy, but they preserve a modification of this. So if you imagine that the green line is the energy isosurface for the continuous energy which you care about, then what symplectic integrators preserve isn't that green line, but they preserve this perturbation, it's like which is in orange. So it's a level set of a slightly modified energy function, and basically the level set of that slightly modified energy function is always close to the level set of the continuous energy function. And so by exactly preserving this discrete or modified energy, you then are guaranteed to stay close to the continuous energy surface indefinitely. And so you see this with these simulations. So here we have some plots of various types of symplectic integrators. It's like, and you'll see that like the midpoint Newmark, variational integrators, and explicit Newmark. So these methods don't exactly preserve the energy. As you can see, there are oscillations, but the oscillations remain bounded for very, very long times. So this is in contrast to a non-variational Runge-Kutta method, like here. And you see that that exhibits energy decay, which is non-physical. So that's the case for conservative mechanics, where you expect the mechanical system to exactly preserve the energy. You might ask, well, what happens if the system is forced or it has dissipation? So that's the second picture over here. And so this black line here represents the benchmark solution. This is how the energy evolves with time. And you see that if you used, again, one of these non-variational Rakuta methods, the rate of energy decay is actually much larger than is physically motivated, if you will. Whereas if you used a modification of one of these symplectic or variational integrators, then the energy evolution more closely tracks the benchmark solution. So it does a better job. And in some sense, it does this because in the limit of zero dissipation and zero energy loss, the energy error is very small. It's like, and there's no artificial numerical dissipation. Whereas oftentimes with stable Rakuta methods, the stability is achieved by sort of introducing a great deal of artificial numerical dissipation. Okay, so let's look at a couple examples. We have the forward Euler, the inverse Euler, and the symplectic Euler methods. Okay, so here Q is the position and P is the momentum. And so this is saying that the position at the new time is equal to position at the old time plus h times the vector field at the old time. Okay, so this is a fairly standard forward Euler discretization. The inverse Euler discretization is similar, except that the vector field is now evaluated at the new time. So what happens then is that with the forward Euler method, everything on the right-hand side you already know, and so in principle you can just evaluate it, and it's a straightforward update. With inverse Euler, you'll see that the unknowns, which are the positions and momentum at the new time, show up on both the left and right-hand sides, and so you get a system of equations which you have to solve, and this is what makes that method implicit. Okay, and then you have symplectic Euler, which has an interesting vector field which is evaluated at the current position but the new momentum. So it's not explicit, but at the same time it's not quite as implicit as inverse Euler. Let's see what happens when you actually apply each of these methods to this model of the solar system described by the n-body problem. So this is with the forward Euler method. And what you see here is that the trajectories are sort of slowly, it's like expanding, and eventually one of the planets gets voted out the solar system. Okay, so you might ask, well, is this something which is due to the fact that forward Euler methods are what they called conditionally stable, which basically means that if you take too large a time step, then even when applied to systems which should decay to zero, they actually end up being amplified instead. Okay, so if you've ever taken a class on numerical ODEs, it's like then you might be familiar with this idea of conditional stability. And if you have, it's like you might also realize it's like that the inverse Euler is unconditionally stable. So let's see what happens when inverse Euler is applied to the same problem. And so now you see that the trajectories are decaying, and one of the inner planets, it's like gets too close to the sun and again gets kicked out of the solar system. But at least you'll see that the energy seems to do energy error below. It's like seems to do a much better job. It's like until such time that you have this ejection event here. All right, so you might ask, well, is this because the solar system is unstable? And it's like the jury is still out about the long-term stability of the solar system. But over the time duration, it's like of these simulations, which are about 100, 200 years, it's like there's a fairly reasonable expectation that the solar system is actually quite stable. So let's see what happens if you apply symplectic Euler. And you can see here that symplectic Euler does a truly wonderful job. It's like it has these closed orbits. The energy error, it's like once the slide comes back, it's like you can see the energy error is much smaller. And so here the energy error is about 10 to the minus 3. And you have these characteristic oscillations in the energy, but the energy error stays bounded. So there is perhaps something going on here, and one might ask, well, what is this geometric structure which is preserved, and how does it yield better numerical results? Okay, so so the approach it's like which my own research takes to the construction of geometric integrators is by sort of bringing to bear it's like the kind of differential geometric and symmetry techniques which arise in geometric mechanics when used to study Lagrangian Hamiltonian mechanics. And in particular, there is a computational version of this, which we refer to as computational geometric mechanics. And the idea is to construct computational algorithms using ideas from geometric mechanics. And in particular, there is what is known as variational integrators, which are based on discretizing Hamilton's principle, which are automatically symplectic and momentum preserving. All right, so you might ask, well, why adopt this approach? And there are certain compelling reasons for this, one of which is that it provides a systematic framework to construct structure-preserving numerical schemes that are consistent with the underlying geometry of the problem. And as we will see, structure preservation can be important from the point of view of stability, accuracy, and efficiency. And more importantly, it's like by constructing methods in this kind of rational way, it provides insights into the discrete analogs of certain differential geometric structures that are preserved by these numerical schemes. All right, so what's the traditional approach to constructing numerical integrators? So the traditional approach, of course, is to perform the discretization at the level of the equations of motion. And examples of these include finite difference and finite element methods applied to the differential equations of motion. And the alternative approach, which is taken in computational geometric mechanics, is to discretize the underlying variational principles. So you might ask, well, what are these variational principles? And so I'll briefly review for you what is called the Lagrangian formulation mechanics. So if you have a Lagrangian L, which is a function of the tangent space to the configuration bundle, which has local coordinates, positions, and velocities, and this is a scalar function, then the claim is that the solution satisfies what is called Hamilton's variational principle. So it says that the integral of this Lagrangian, when you vary it, so this is what this delta represents. It represents a variation of that action integral. So then it's stationary. Okay, so what this more or less means is that if you have a curve, which has a prescribed initial and final point, then the actual trajectory which the system describes is that which has an action integral which is stationary when you vary that curve subject to the same fixed endpoint conditions. So this turns out to be equivalent to what are called the Euler-Lagrange equations, which are given here. And when you have the Lagrangian of the form kinetic minus potential energy, then you can check that this reduces to Newton's second law. And this way of thinking about mechanics has the advantage that it is coordinate independent. Okay, so this is independent of the choice of coordinates, and as such, it's a very natural way of describing mechanical systems, particularly when you're working on manifolds. All right, so you can ask, well, how do you go about discretizing something like this? And so what you do is you approximate the tangent space, the position and velocity space, by 2 copies of the position space of the configuration manifold. So one way to think about this is that these 2 copies of positions represent the position of the system maybe at 2 nearby times. And then what you want to do is to look at the diagonal group action of some Lie group. It's like on these pair of configuration manifolds. And this is going to be related to the thing we saw earlier, where I said that symmetries are related in some way, shape, and form to conservation laws. So we'll see this show up in practice. All right, so in any case, you have a discrete Lagrangian now, which is a map from 2 copies of the configuration space to the rails. And you can think of this as a generating function of some discrete time flow map. So a particularly simple choice of such a discrete Lagrangian is given by the following expression. So here what you see is that you have a midpoint approximation of the position and then a finite difference approximation of the velocity. Okay, and then so that's just the Lagrangian, and then you're multiplying this by h. So the best way to think about this is that this is an approximation of a piece of the action integral over a small time step h. Okay, and that's and in particular this is the midpoint rule. It's like applied to that. All right, so if the discrete Lagrangian then can be thought of as a piece of the action integral over a small time interval, then you can construct what is called the discrete action sum, which involves summing up these discrete Lagrangians over the entire interval. And this, of course, gives you an approximation of the action integral. Okay. All right. Then the discrete version of Hamilton's principle states that you have a solution curve where the discrete variational principle is stationary. Okay. And so this is the picture. It's like one should keep in mind that if you have an initial point and a final point, the trajectory, which is actually described by the mechanics, is that for which if you allow the curve to vary slightly subject to the endpoints being fixed, then the action integral doesn't change to first order in the variation of the curve. So you discretize this by essentially sampling the trajectory at a bunch of points at a bunch of different times, and then you require that the discrete action sum, it's like which is obtained by summing up the discrete Lagrangians or over sort of the sequence of pairs of points, that doesn't change. It's like when you allow these points to vary slightly, subject to, again, the endpoints being fixed. All right. So, all right, so you extremize the discrete action sum over, it's like the sequence of points q0 to qn, and you want that, the variation of the action sum is stationary with respect to these things. All right? And this implies that you get an equation of this form, and you require that the variation of the initial point and the final point is vanishes because those points are fixed. And so when you use it's like the vanishing, it's like variation endpoint condition, you end up getting what are called discrete Lagrange equations, which are given here, where this phi here is the discrete time flow map. Okay. All right, so why is this significant, and what does this approach buy you? So one way to see it's like what this approach buys you is to consider what is called the exact discrete Lagrangian, which is the following object here. You specify a position at time tk and at time tk plus 1, and then you write down the action, it's like over some curve, where that curve q is a solution of the Lagrange equations, while satisfying these boundary conditions that q at tk is equal to qk and q at tk plus 1 is qk plus 1. So of course this is something which is in general difficult to compute, because in order to compute this you need to solve some Lagrange boundary value problem, and of course if you could do that, then it isn't really necessary to construct a numerical approximation. But nevertheless, this object exists, and this choice is related to what is called Jacobi solution of the Hamilton-Jacobi equation. And essentially what happens then is that this is a generating function of the exact solution flow. Okay, so there exists, if you will, an exact discrete Lagrangian, which if you were to plug it into the discrete Lagrange equations, would give you the exact time h flow map of the original Lagrangian system or Hamiltonian system. So you might ask, what exactly is symplecticity? So in order to understand that, we have to consider what is called Hamilton's equations. So these are expressed in terms of position and momentum coordinates, and expressed in terms of a Hamiltonian, which is a scalar value function, which depends on the position and momentum. So if you adopt a coordinate system which has position and momentum variables, then there is what is called the canonical symplectic form, which is given by this 2 form, and it has a matrix representation given by this 2n by 2n matrix. So, so it turns out then that you can write down Hamilton's equations expressed in terms of z dot, in terms of a Hamiltonian vector field, which is this symplectic matrix J multiplied by the gradient of the Hamiltonian. Alternatively, you can write this in the sense of differential forms by taking a 2 form and putting down a vector field xh, and then a arbitrary vector field v, and then requiring that this is equal to the exterior derivative. It's like paired with this arbitrary vector field v. So this implicitly gives you a way for solving for this Hamiltonian vector field xh. So this is a more intrinsic way, if you will, of describing these equations which we have here in coordinates. Okay, so in any case, once you have that, there's a corresponding discrete version of this, and this is done by introducing what is called a discrete fiber derivative. It's a map from, again, 2 copies of the configuration space to the cotangent bundle, which is expressed in terms of positions and momenta. So the map has this explicit form where this d1 represents a partial derivative of the discrete Lagrangian with respect to the first variable, which is q sub 0. All right. So once you have that, you can introduce a discrete symplectic form by pulling back the canonical symplectic form via this fiber derivative. And after doing the calculations, you end up with an expression like this. So this is the discrete symplectic structure, which is preserved by one of these variational integrators. Okay, so in any case, one might ask, well, what does this buy you? So if you look at the phase portrait for the planar pendulum, and you start off with a bunch of points, it's like as initial conditions, which is represented by this cat-like initial condition. Then what happens as you advect by the flow is that the shape gets distorted, but the actual area enclosed remains a constant in motion. Now, if you were to try to do the same thing with explicit Euler, you'll find that the phase volume actually increases as you keep applying explicit Euler, whereas in contrast with symplectic Euler, this phase volume is again a constant of the numerical method. Okay, so this is one example of how numerical methods can preserve its like geometric structures which are present in the continuous problem. So this is another picture of what symplecticity means in the context of the planar pendulum phase portrait. So again, with some sort of initial data, you'll find that there's this stretching phenomena, but again, the volume or the area enclosed remains constant, and the same is true here. It's like with this different set of initial conditions. All right, so so now that's the same plot here, but for the various kinds of numerical integrators you could use. So this is what happens with explicit Euler, and you see that in explicit Euler the phase volume increases. With symplectic Euler the phase volume is a constant. With implicit Euler, it may not be so obvious here, but it's much more obvious with this, that the phase volume is contracting. Okay, second order Runge-Kutta method, which is not a symplectic method, has this phenomena where the phase volume is increasing. Verlet, which is a symplectic integrator, has this volume preservation property, as does the midpoint rule, which is given here. Okay, so these are just some geometric phenomena which are preserved by some class of numerical methods and not others. So, so the third part of the picture then is, well, what happens to this relationship between symmetries and conservation laws. So perhaps it's worthwhile to describe at some level this idea of momentum maps. So a momentum map formally is a map from the cotangent bundle, which is positions and velocities, to the dual the Lie algebra. And the basic point is that this momentum map is a generalization of the familiar conjugate momenta one sees in Hamiltonian mechanics. There is what is okay, so if you have a mechanical system that is invariant under the action of a Lie group on this configuration manifold, you can define this momentum map in the following way. And the claim is that there is a discrete version of this, which is given by this J sub D, which is defined again in this way. All right, so there's an example of a momentum map if you have the rotation group acting on sort of three-dimensional space by matrix multiplication in the following way. Then essentially what you're looking at is you're looking at the component of the conjugate momentum in the direction of what is called the infinitesimal generator. So essentially what the infinitesimal generator does is that it looks at a small part of the group orbit which goes through a point, and then it looks at the, it's like the tangent to that curve. Okay, so the infinitesimal generator is given by this expression, and from that you can conclude that the associated momentum map associated to rotational invariance is given here, which basically tells you that the usual expression for the angular momentum is the momentum map associated with rotational invariance. Okay, so before I do that, it's like one might ask, well, what does this kind of thinking buy you? And this, in some sense, gives you a systematic way of constructing numerical methods which preserve or respect the symplectic structure as well as momentum preservation properties, and you can construct this to arbitrarily high order. Okay, so this is in contrast to what happens if you had a Runge-Kutta method. So Runge-Kutta methods, which you might know, it's like a fairly general class of numerical integrators for systems of ODEs. And they're defined in terms of these coefficients, the aij's and the bi's. All right, so for a Runge-Kutta method to be symplectic, it has to satisfy this system of constraints. And of course, this is not a particularly constructive way of constructing a numerical method. Okay. So this is in contrast, it's like to the more systematic tools, it's like which we'll be developing in the context of variational integrators. So in any case, this generalized approach, which we will show, leads to a bunch of generalizations, including to, well, what happens if the configuration space is a Lie group. You can look at what happens when you have multiple timescales, and you can also look at what happens if you construct sort of spectral type discretizations. Okay. All right. So let's look at the case for the rotation group, because that's an important class of examples. So there are several ways of coordinatizing, if you will. It's like the rotation group. The simplest one, which is perhaps it's like most oftentimes taught in a analytical mechanics class, is what is known as Euler angles. Okay, and so the problem, if you will, is like with Euler angles are that they're a local coordinate chart and exhibit singularities, sometimes referred to as gimbal locking. And in particular, they require a change of coordinates or change of charts to simulate very large attitude maneuvers. So if you have a rigid body which is tumbling, it's like in a dramatic way, then you'll spend a lot of time changing coordinate charts. Another approach which is quite popular in the engineering community is to use what are called quaternions, and in particular to identify rotations with the unit 3 sphere. It's like in the quaternions. And the advantage, if you will, of this approach is that the condition of staying on the unit 3 sphere is relatively straightforward. One could simply use something like reprojection. And the potential disadvantage, if you will, of unit quaternions is that the 3 sphere is a double cover of the rotation group, And so this may cause topological problems when you're trying to do optimization. All right. So finally, it's like, it's like the third approach is to look at rotation matrices, which are of course 3x3 matrices with a 6-dimensional orthogonality constraint. So you might wonder, why would you ever want to do this? Because that's an extremely high-dimensional embedding space, it's a 9-dimensional embedding space with a very high-dimensional constraint, and 6-dimensional orthogonality constraint. But the claim is that if you introduce what is called the exponential map, then you don't really have to work, it's like in 9 dimensions, with the 6-dimensional constraint. The exponential map somehow respects that automatically. All right, so what's the basic idea behind this? So the basic idea is that if you are in a Lie group, there is always an associated Lie algebra, which is the tangent space to the identity of the Lie group. The Lie algebra is always a linear space, okay? And you can locally relate the Lie algebra and the Lie group with an exponential map. So in particular, if you're looking at the rotation group, then the rotation group has as its associated Lie algebra the space of skew-symmetric matrices, and clearly the space of skew-symmetric matrices is a linear space. If you add skew-symmetric matrices together, they stay skew-symmetric, okay? And one way to get from skew-symmetric matrices to the rotation matrices is the matrix exponential. So if you take the Taylor expansion, it's like for the exponential, and you interpret it, it's like in terms of matrices, then this gives you a well-defined map, which will always map, it's like skew-symmetric matrices to rotation matrices. All right, so now it's like if you want to have a curve, it's like in the Lie group, you can write it as the exponential of some curve in the Lie algebra multiplied by the initial point on the group. Okay, so this gives you a way of lifting interpolance on the Lie algebra to interpolance on the Lie group. And we know how to construct interpolance on the Lie algebra because it's a vector space. Yep. And so you can lift this, it's like using some sort of exponential map. And when you write down it's like curves in this way, then clearly they automatically stay in the rotation group without the need for reprojection constraints or coordinates. And you can also prove that the order of accuracy of the method you develop turns out to be independent of the choice of retraction, as the variational principle you end up writing down is kept at the level of the Lie group, and the retraction is simply used to locally parameterize the group. So, yeah. All right, so let's see how this works in practice. So I'm going to consider what's called the 3D pendulum. So this is basically a rigid body which is pinned at a point which is distinct from the center of mass. It has 3 degrees of freedom, and what's interesting about this is that even it's like under just gravitational interactions, it exhibits surprisingly rich and complex dynamics. So this is a physical realization of a 3D pendulum. This is the triaxial attitude control testbed at the Attitude Dynamics and Controls Lab at the University of Michigan, run by Harris McClamrock and Dennis Bernstein. Okay, so it looks a little bit like a TIE fighter. It's like with these, it's like fans in the side. In any case, you can write down a mathematical description of this in terms of Lagrangian mechanics. So you write down a kinetic energy term and a potential term. Okay, and then you can, using these Euler-Lagrange type techniques, you can write down the equations of motion. So you can do it's like a simple discretization of this, and this involves essentially, this is obtained by using linear interpolation together with the trapezoidal rule, and you end up with these equations of motion here. And so in order to guarantee that the method stays on the Lie group, you basically write down an ansatz, okay? So for the update. So this Fk you should think of as being the sort of near to identity rotation, which takes you from the current attitude to the attitude at a later time. It's essentially, again, the relative rotation between 2 states of the rigid body. And because of the fact that it's a near to identity rotation, you can write this as the matrix exponential of some skew-symmetric matrix. Okay, and the hat map basically is a Lie algebra isomorphism which maps 3 vectors to skew-symmetric matrices. And then there's what's called the Rodriguez formula, which converts this equation, which normally you would have to solve. It's like with the constraint that Fk is in the rotation group, you can rewrite it now in terms of little fk. Little fk is nothing more than a 3 vector. So since big Fk is the 3 vector mapped to a skew-symmetric matrix exponentiated, this thing is always going to be a rotation matrix. And so when you use it in this last equation here, it says that the the rotation matrix at the new time is the rotation matrix the old time times this sort of near the identity rotation. This guarantees that the rotation matrix at the new time is indeed a rotation matrix. All right. So you can see what happens when you apply these methods to a 3D pendulum. So this is just, again, it's like a rigid body with a fixed point which is not coincident with the center of mass under gravity. Okay, so it's not being forced except by gravity, and you'll see that it has this extremely complicated, extremely large rotational dynamics. And so this is basically telling you that if you try to use local coordinate charts on this problem, you would face a serious impediment because you would spend all your time changing coordinate charts. And even if you did, it's like you oftentimes find that you'll have very, very poor numerical results. So one of the challenges, if you will, in describing dynamics, it's like on Lie groups, is to develop numerical methods which are well defined on the full configuration manifold. So the next example we're looking at is the interaction of 2 dumbbells. So these are basically 2 spheres that are connected with a rigid massless rod. They're interacting, it's like via their mutual gravitational interactions. So this is the flyby of 2 dumbbells, and you'll see that they interact under their mutual gravity. So this slide is meant to give you a sense as to what happens depending on your representation of the rigid body dynamics, be it in terms of unit quaternions, which the engineers favor, or with Euler angles. So you'll see that if you look at the total energy error, it's like in the representation using quaternions, there are slight kicks, and so the energy is not constant, but it certainly does a much better job, it's like, than what you see with Euler angles, where these very substantial deviations in the total energy. And in a sense, this is due to the fact that the coordinates associated with Euler angles is like exhibit singularities, and so as you have very substantial rotations, the conditioning, it's like, of those coordinate charts become very poor, and that manifests itself in these kind of numerical errors. On the other hand, if you were to use these Runge-Kutta methods with the rotation group, you'll see that it does a much better job. And that again speaks to the fact that the working directly, it's like in terms of the rotation matrices, yields much better sort of, it's like global sort of error properties, if you will. And so you'll see that there's an energy error, it's like, but nevertheless it's much smaller. There's this here represents the deviation, it's like, of the method of the rotation group. So there is this drift, if you will, off the rotation group because you're working, it's like, on these 3x3 matrices. All right, so now it's like this is an example of what happens if you would combine a Lie group variational integrator, which is in particular symplectic integrator, together with the rotation matrix representation. And again, you see that it's like it does a much better job in terms of keeping the total energy constant. And in addition to that, it's like the energy error is also much smaller. And the error, it's like in sort of in the rotation matrix is again, it's like much smaller as well. Okay. All right. This plot here tells you the deviation in the total linear momentum and the total angular momentum. So now we're going to compare it's like the effect of the various kinds of structure preservation and how they interact when you're dealing with Hamiltonian systems, which are symplectic, but which are also it's like evolving on some sort of curved space, in particular the rotation group. So our Lie group variational integrator is a Lie-Sturmer-Verlet method. So it is a second-order accurate symplectic Lie group method. So it's very, very natural then to compare it with other second-order accurate methods. In particular, there is the explicit midpoint rule, which is neither symplectic nor Lie group method. There is the implicit midpoint rule, which is symplectic, but is not a Lie group method. And there's, of course, the Crouch-Grossman method, which is a Lie group method, but not symplectic. Okay, so those are sort of some natural choices. And let's see what happens. Okay, so these are Runge-Kutta, symplectic Runge-Kutta, sort of a Lie group method, and then the Lie group variational integrator, which is both a Lie group and symplectic method. Okay, and so if you look at the red line, which is our Lie group variational integrator, you'll see that the total energy error is extremely small, as one might expect. But what is interesting is that the symplectic method, which doesn't stay in the Lie group, actually has a much larger energy error than the Lie group method, which is not symplectic. And so that's sort of suggesting that drifting off the Lie group, it's like exhibits an energy decay, which symplecticity in and of itself doesn't address. Okay, if you look at the mean total energy versus time step, you'll see again that these Lie group variational integrators, it's like perform the best in terms of energy error versus step size, and the same is true. It's like of the orthogonality error. So both the Lie group integrators and the symplectic Lie group integrators do a really good job of respecting the sort of orthogonality error. And you might ask, why is it that the error increases as you decrease the time step? And that's really because there's an issue of round off. So when you multiply two matrices which are orthogonal to machine precision, there is an accumulation of round-off error. And so the more times you have to update, which is true when you're taking smaller and smaller time steps, then these errors accumulate. And this is what you're seeing here. So finally, you can ask, well, what is the sort of CPU time versus step size? And again, it's like these sort of Lie group variational integrators do a very, very good job because it's really a Lie group version of Sturmer-Verlet, which turns out to be explicit when you have separable Lagrangian Hamiltonian systems. All right, you can also apply this to other problems. So in particular, you can apply this to what happens with asteroids. And so asteroids are approximated by rubble piles, which are basically hard sphere models, or by simplicial complexes. And then the force evaluations are performed using fast multiple methods or polyhedral, it's like potential techniques. So the main computational cost is really the cost of this force evaluation. And the advantage then of these Lie group Sturmer-Verlet variational integrators, which we've developed, are that they only use one force evaluation per time step, and they are only implicit in the attitude, and they converge in 2 to 3 Newton steps. Okay, and so this was used by a colleague of mine, Dan Shears, it's like at the University of Michigan, to accurately simulate binary near-Earth asteroids with this number. It's like, and this turned out, this result showed up on the cover of Science magazine several years ago. All right, so this is a simulation of this binary asteroid simulation, and what is nice about it is that it's taking a bit of time. But what is nice about it is that it is the most accurate model we have, if you will. It's like of these asteroids. It's limited by our observational precision. And you can see that it does a really nice job. It's like of simulating the binary asteroid interaction. So this is of astrophysical significance because most asteroids come in these asteroid pairs. So another thing it's like you can do, it's like with these kind of Lie group variational integrators, are to look at what is called under-actuated control, So this is an example where you have, again, it's like this 3D pendulum, but imagine you're only allowed to control the center of mass. So if you control the center of mass, of course, has to move. It's like on the sphere. So you really have 2 degrees of freedom, if you will. And the missing degree of freedom is sort of rotation about, it's like the axis of the 3D pendulum. And of course, to make things interesting, you can ask, well, is there some way to control the rotation about this axis when you only allowed direct control over the center of mass? And so this is what is meant by under-actuation. You don't have full control over all 3 components, it's like, of the problem. So that's an interesting, it's like, exercise in what is called geometric control theory. And this simulation shows, it's like an example of how you can use just the control of the center of mass together with this kind of geometric nonlinear coupling to actuate control about this sort of directly controllable direction. So it turns out that it's like this is related to what is called reduction theory, and in particular there's some notion of curvature, and if you have if you're trying to do this kind of under-actuated control, it's like, then if you want to do this as efficiently as possible, then what you want to do with your control loop is to encompass a region of high curvature. And so this is an example where the point you start off with is a region of low curvature, and the region of high curvature is far away. And so, what you see in the simulations is that the trajectories which the 3D pendulum actually, it's like, undertakes, it's like, in order to achieve this rotation, is quite aggressive. This is in contrast to this case where the shape of the 3D pendulum is different, and in this situation, it's like the region of high curvature is close to where it's like the pendulum starts off with. And so what you see then is that the motions which that pendulum takes is now much more subtle, it's like, than was the case in the first example. So what this sort of tells you is that in these examples, where the region you're starting off with is a region of high curvature, then many of the traditional local techniques involving Lie bracket expansions work well. But if you're in this case where you're far away from the region of high curvature, then you need to really develop sort of these kind of numerical techniques for doing these kind of geometric phase type controls. So let me say a little bit now about, well, what happens if you work with things which are not Lie groups, but what are called homogeneous spaces. So the simplest example of a homogeneous space is perhaps the 2-sphere. So the 2-sphere is related to a rotation group because the idea is that you can get from any point on sort of the 2-sphere to any other point on the 2-sphere through an appropriate rotation. So another way to sort of think about this is that if you have a curve, it's like on the surface of the sphere, then there's a sense in which you can reconstruct that curve by lifting it to a curve on the space of rotations. And this curve in the space of rotations then acts on some initial point, and that sweeps out a curve, it's like, on the sphere. Okay, so this is what is meant by a homogeneous space. A homogeneous space is any space which has a group acting on it in such a way that you can get from any point on the homogeneous space to any other point on the homogeneous space through an appropriate group action. Okay. All right. So the condition that you stay in the sphere, you have this unit sphere condition, sort of constrains the variation in the variational principle. Okay. So you can write it in the following way, and then you can write down a Lagrangian for, it's like some Cartesian product of 2 spheres, and the Lagrangian has this kind of form of kinetic minus potential energy. All right. So with the spherical pendulum, it's like you can write down a method which looks like this, and the double spherical pendulum gives you a method like this. So the advantage, if you will, of these equations are that they're even though they're implicit, they can be solved using what is called fixed point iteration. and it only requires about 5 to 6 iterations to reach machine precision. So the advantage, if you will, of fixed point iterations is that unlike trying to solve a system of nonlinear equations using Newton's method, you don't have to construct the Jacobian, which is a very expensive thing to construct in general. So fixed point iterations in some sense are cheaper to implement. All right, so in any case, when you develop these methods, you can apply them to, for example, this double spherical pendulum here. And this is a nice numerical method because it only requires, or it only uses 2 degrees of freedom for every copy of the sphere it has. So in this case, it has 4 degrees of freedom. But it doesn't, it doesn't blink when you have the pendulum arm. It's like swinging up from the north to the south poles, so there's no worry about the coordinates. If you were to use sort of projected coordinates, it doesn't suffer from the problem. It's like with spherical polar coordinates, where if it is in the sort of the north or south facing directions, it's like you have coordinate singularities. So this gives you a very robust method, which is still requires only a minimal number of degrees of freedom. Okay, so traditionally, the way people would try to simulate this is by using just embedding, it's like the pendula, it's like in 3-dimensional space, and then imposing unit length constraints. So that has been the traditional method, but this uses a minimal number of degrees of freedom, but still has all these nice global properties. So you can also do sort of a generalization into 3-body problem. It's like on the sphere, and you can then consider what happens if you try to generalize these kind of problems to field theories. Okay, so this leads to this idea of multisymplectic geometry, and what happens then is that you consider the base space, which is this flat horizontal space here, and you typically think of this as n+1 space-time, and then you have the configurations over that. Okay, so you think of this as space-time, and the vertical direction as being the fields, and so what happens then is that you look at sections of this configuration bundle. So a section is a fancy way of saying that if you have some initial, position, it's like in time point, it's like then you want to tell me, it's like what the field value at that position in time is. All right, so that's an example of a section, and so you see this this surface, it's like on top of space-time, is basically telling you what the field values at every point in space and time is. And then you can consider what is called the first jet extension, which is basically the partial derivatives of the field values in both the space and time directions. Okay, so if you have that kind of setting, and you can introduce what is called a Lagrangian density, which is a map from the first jet bundle to an n+1 differential form. So what basically happens then is that the way you compute this is that first you compute a section, and a section again is a prescription for what the field values are at every point in space and time. Then you look at its jet extension, so you augment to that the first derivatives of the fields with respect to space and time. This is in the first jet bundle. You can write down what the Lagrangian density, it's like, for that is. The Lagrangian density, it's like, given this is of course an n+1 differential form, which you can integrate over an n+1 space-time region to give me then a action integral. Okay, then Hamilton's principle states that the variation of the action integral subject to fixed boundary conditions is stationary. So this is really a very natural generalization of what we've seen before in the purely mechanics case. So in any case, given this idea of multisymplectic geometry, you can extend them to a class of other problems. So I'm going to look at a few toy examples on geometrically elastic, exact elastic rods, the elastic strings, and micromagnetic simulations. So you can think of this as arising from a variational multisymplectic scheme where you use a tensor product discretization of space-time. So that basically means that you discretize space and you discretize time separately, and then the discretization of space-time is obtained by just taking the product of this. All right, so in any case, so this is an example now of a approximation, if you will. It's like of a rigid rod, And really, in practice, what this is done is that it's a chain of something like 10 spherical pendula, and with a term which penalizes relative angles between, it's like the spherical pendula. So it's like a bending stress. So you can see that it does a reasonably good job. It's like approximating what you might see. It's like if you were to take a rigid rod, or sort of near rigid rod, it's like, and just snapped the end, it's like, and you'll see this kind of chattering effect. All right. So you can also do this for strings. So this is a combination of these two sphere, it's like simulations together with a term, it's like, which tells you the length, it's like, of the string between two adjacent points. And the advantage of decomposing the configuration space into essentially the two sphere cross positive rails is that this allows you to deal with situations where, for example, the bending stiffness is different from the stretching stiffness. So if you're dealing with multi-scale problems, if you will, then this kind of decomposition, it's like into the components of the configuration space which respond differently, it's like, to various sources of stress. That's a very natural thing to do. And then finally, this is a micromagnetic array simulation. What you might see if you had a lot of sort of micromagnets, it's like, and they were interacting with each other. So the nice thing about all these simulations is that they're all sort of based on the same code base, and so these two-sphere simulations are really sort of quite general. All right, so other things, it's like, which we might have time to talk about as the course progresses, is this role of symplecticity in uncertainty propagation. So one of the things one sees, if you will, is that increasingly we're not just interested in numerical methods which give you good accuracy. We're interested in seeing, well, what happens if there's some uncertainty in the initial conditions and how that uncertainty propagates forward in time. Okay, so so the point is that if the flow is symplectic, in particular, it's volume preserving. But the claim is that symplecticity is somehow a stronger condition than volume preservation. And one way to see this is that there's what's called Gromov's non-squeezing theorem, which arises in symplectic geometry. And it basically says that there's a lower limit to the projected volume on matched position momentum planes that depend on the initial volume of this uncertainty region. So it's essential then, it's like, to when you're trying to quantify the uncertainty and how it's propagated in a Hamiltonian system, that you use a symplectic as opposed to simply a volume preserving method instead. So the essential idea then is to solve the Liouville equation to characterize the fluid distribution. And then you look at the space-time, and you augment this with additional directions corresponding to sort of the random variable spaces. And then instead of using trajectories or sample points to compute statistics, as you do with Monte Carlo, you use these trajectories or sample points to reconstruct the distribution. And then this uncertainty distribution is vectored by the flow, and the advantage then is that this can be done in parallel, and you can do this reconstruction, if you will, efficiently using a combination of collocation and spectral interpolation. So, so this raises the question of, well, what happens with how do you represent probability distributions in curved spaces? And of course, the usual way to represent probability distributions on flat spaces is to look at moments of the distribution, which are essentially the expectations of the polynomials. So the expectation of the constant is going to give you things like the mean. The expectation of it's like degree 1 polynomials will then be related to variance and so on. And so you want to do something similar, if you will. But the problem with using moments of a distribution on a curved space is that they oftentimes don't make sense. So what's perhaps better, and this is what we try to do, is to attempt to generalize things like Fourier expansions And you can do this, it's like using what is called non-commutative harmonic analysis. So there's a way to construct, it's like a basis for L2 functions, it's like on some group, by looking what are called the irreducible unitary group representations. So basically what it is that you consider a group representation. So this is a map from the group to the general linear group in such a way that it is a homomorphism, it's a group homomorphism. So it means that this map respects the composition, it's like on the two spaces, and is compatible with it. And then the Peter-Weyl theorem says that if you look at these L2 functions in the group, these are obtained, it's like by the following thing. So this is a fancy way of saying that, okay, you have a map from the group to some matrix group. And if you would look at the components of the matrices, and you would think of them then as scalar valued functions on the group, then these together, it's like form a basis for L2 functions on G. This is basically the content of the Peter-Weyl theorem. And what happens then is that if you have a compact Lie group, or if you have a Lie group with a bi-invariant Haar measure, then all the standard techniques from computational harmonic analysis generalize. So in particular, you get a fast Fourier transform, you have a Plancherel theorem. And so you can develop very, very fast techniques on these spaces. And in particular, it's like when you do this on the rotation group, you recover, of course, the spherical harmonics. And there are fast spherical harmonic transforms you can use in this problem. So in any case, it's you can then use these methods to represent probability distributions on the rotation group. And this is our attempt to visualize this. So you should think of this, if you will, as an intensity map, which tells you something about each of the columns, if you will, it's like of the rotation matrix, right? So it's telling you, it's like, how concentrated, if you will, it's like each of these columns are. So they start off, it's like in some sort of uniform Gaussian-like distribution, and as it evolves in time, it's like you have, it's like uncertainty, it's like somehow being spread out. It's like in some directions, but concentrated in others. Okay. All right. So anyway, so let me just summarize by saying that variational integrators are symplectic, and they can be made to have arbitrarily high order, and they conserve a discrete analog of momentum, and that you can generalize these methods to nonlinear configuration spaces, in particular Lie groups, for example, the rotation group, or homogeneous spaces like the two-sphere, as well as other manifolds. And you can do this in a global and computationally efficient manner. I've also sort of alluded to how you might generalize this to Hamiltonian PDEs. And there is a exact generating functional for multisymplectic TDE. And if you wanted to construct methods which preserve momentum, then it turns out that there's some notion of group equivariant function spaces which are relevant. Okay, so these are some references which we used, it's like in this presentation. And so again, this is meant to give you a flavor, if you will, for some of the methods which fall into this general framework of geometric numerical integration. As the quarter progresses, we will explore, it's like, several of these things. And there is an opportunity for you then to do a project of it's like on a topic of your choice, which allows you to focus to a greater extent on, it's like an area which perhaps resonates with your interests. And usually that involves either going deeper, it's like into some of the numerical methods we've studied, or perhaps applying those numerical methods to an application of your choosing. So let me just stop here for today. Thank you.